Okay, the last piece of the puzzle regarding alpha, beta, type 1, type 2 errors, decisions, truths is a picture of how they are all interrelated. So we're going to look at two separate pictures, one where we have an upper tail test and one where we have a lower tail test. They're exactly the same picture, just mirror images of each other. They're the same circumstances. We just need to look at both because sometimes we get in our heads that everything is about the upper tail, but it really depends on the circumstance. So let's start with a normal model. And let's say that this normal model represents all the possible samples for a specific situation. So we're going to hypothesize that a population has a particular parameter p sub 0. Okay, so let's just pick a middle here. So I have some situation for which I've defined a null hypothesis parameter. That's why I'm calling it p sub 0, because this is the p that's defined in the null hypothesis. It could be 20%, it could be 80%, it could be 55% of successes for some situation. Okay, so I set an alpha level. Okay, so if it's an upper tail test, I'm going to set an alpha level on the upper tail. That alpha level is changeable. It could be 5%, it could be 1%, it could be 2%, it could be 10%, depending on the situation. So, let's assume first that the null hypothesis is true. Okay, so this is a picture of the truth. The null hypothesis is true. If the null hypothesis is true, and we draw a sample, and the sample lands in this tail to the right of the alpha level, we would reject. And if the sample lands down in this lower portion, we would fail to reject. So down here is fail to reject territory. If the null hypothesis is true, that would be a correct decision. So if the null hypothesis is true and we got a sample in this section down here, then we would fail to reject and we would make a correct decision. So that's a good thing, thus the smiley face. On the other hand, if our sample landed down here in the tail somewhere, I should say up here in the tail somewhere, that would be reject zone. So we would reject the null hypothesis, and that's wrong, because if the null is really true and I get a sample out here and reject, I will have made a wrong decision. So this is type 2. So what's out here is alpha. This is alpha. And the probability of that happening is the type 2 error probability. So this is associated with type 2 error. So if the sample lands here, I'm going to make a bad decision. If the sample lands over here, I'm going to make a good decision. Okay? On the other hand, let's say that I define a null hypothesis as p sub 0. And it's really false. Okay, so a situation. Let's say that my p sub 0 is the percentage of students who bring their lunch to school. I know I've worn that one out, but it works. And it's like 30%. So let's say that I thought it was 30%, but it turns out, unbeknownst to me, that the percentage of students who bring their lunch is actually higher than that. So instead of this p not being, instead of the true p being at 30%, let's say it's really higher. Let's say it's like 65%, which means truthfully, even though I think this is true, I'm claiming this, in reality, like 65% of students bring their lunch. So the truth actually is over here somewhere. So instead of lining up with 30%, I should be lining up with 65%. So that null that I assumed was true is really false. So this is a picture of if the null is false. So it's not really 30%, it's really much higher at 65%. So this is what's really going on, but this is what I believe. This is what I've claimed, this is what I believe. Okay? If I pull a sample to the left of this alpha level, I will fail to reject. Okay? This is fail to reject zone because it's to the left of the alpha level for an upper tail test. Because I think this is the truth when this is really the truth. So this is fail to reject zone, and that is associated with the type 2 error. Because the null is really false, but I didn't reject it because I thought this was the truth. So this is a mistake. If I have a sample that lands down here, I'm going to make a wrong call because I think this is the truth. On the other hand, if my sample lies up here somewhere, this is reject zone. So if a sample lands up here to the right of the alpha level, if I get a sample over here somewhere, then I'm going to reject a false hypothesis. That's a good decision. That's what I'm trying to get at in a hypothesis test anyway, is to show that something has changed. So this is power. So the area under this curve is power. The area under this tail right here is your type 2 error. This is beta. The area up here at power is 1 minus beta because the area under this tail and the area under all of this have to equal a whole area of 1. The alpha level, remember, is still right here. So the area up here above this tail is your type 1 error chance. And I wrote something wrong. Did y'all catch that? I wrote a 2 here. That should be a 1. I don't know what I said. I hope I said 1 when I was there. Okay, so the interrelationship between alpha and beta is alpha's on one end of a correct hypothesis and beta's on the wrong end of the other end of an incorrect hypothesis. And alpha and beta work together in some interesting ways. Okay, if alpha moved down, so if the alpha level moved to the left, so if I made it a 10% alpha test instead of a 5% test, so let's say I moved it down here a little bit. If I move alpha down, it's going to make the area under this curve, under this tail here, bigger, which means I'm going to increase my type 1 error. So bigger alpha means bigger type 1 error because those are equal things. And notice that down here, this tail would get smaller, so type 2 error probability would go down. So when the probability of one error goes up, the other one goes down. So there's got to be some sort of a compromise between the two. You move alpha down too far, then you increase your likelihood of having this type of error. If you move alpha up too far, you increase the likelihood of type 2 error. So there's got to be some sort of a middle ground between those two, and the goal really is to make power as big as we possibly can. There's only one way to make both of these areas get smaller at the same time. If I want to decrease my type 1 error and decrease my type 2 error at the same time, the fix for that is to get a smaller standard deviation. Because if we had a smaller standard deviation, we get a skinnier, taller curve, and we get less stuff in this tail. That would make this a skinnier but taller curve, and we'd have less stuff in this tail, so the probability of type 1 and type 2 error would both get smaller. The way to make that happen is to increase your sample size. Okay, let's take one more look at it. But let's look at it from a lower tail perspective this time. So same gist. So I have some truth that I believe. Okay? So there's some population parameter, like the percentage of people who actually wear their seatbelts. So let's say that's P0. And let's say I make a claim that the percentage of people that wear their seatbelts is 70%. And let's assume that H0 is true. So the percentage of people who wear their seatbelts really is 70%. Okay, but somebody believes it's actually lower. that there really are less than 70% of the people. So they do a hypothesis test. And it's a lower tail test because they think it might be lower. So in this case, in a lower tail test case, to get a sample here would be a good decision. That would be saying that we failed to reject. A correct hypothesis, that's a correct decision, that's a good decision. But if we got a sample that landed here, below that alpha level, below that threshold, farther out in the tail, we would reject, and that would be a wrong decision, and the probability of that happening would be a type 1 error probability. So if we have a 5% alpha level, we have a 5% chance of making a wrong decision, a type 1 error. Okay, well, let's say that H0 is not really true. That in fact, less than 70% of the people really wear their seatbelts. I don't know that because I think this is true. Let's say that only 50% of people wear their seatbelts. So in actuality, that curve should be sitting lower on the number line than it is. And instead of P naught being 70%, P naught ought to be 50%. How much lower it is affects the areas under this curve. If H naught is false, then anything to the left of the alpha level would be reject zone. Anything to the right of the alpha level would be not reject zone. To have a false hypothesis and reject it is good. That's power. That's what we want to be able to do, is to convict the guilty. On the other hand, if we fail to reject a false null, that's type 2 error. Notice the area on this one looks bigger than the last one, and that's why you really can't calculate the beta, because beta is the probability of being in this type 2 area, and how big that area is depends on how far off your claim and your null hypothesis really is. If your claim is really far off, then you have a lower probability of getting a type 2 error. But if your claim is pretty close to what the truth is, then you have a much bigger chance of getting a type 2 error. So the area here, beta, is complicated because it depends on how wrong your null hypothesis is. And of course, power down here, beta plus 1 minus beta would equal the whole area, or 1. If you move your alpha level up, it's going to increase your type 1 error, and it's going to decrease your type 2 error. If you move your alpha level to the left, it's going to decrease type 1 error, increase type 2 error. You can't change one without changing the other in the opposite direction. So the only way to make both of them smaller is to get taller, skinnier graphs, which you can only do with a bigger sample size. All right, last piece, and we're going to be done. So just big ideas. The goal is to reduce error as much as possible. We don't want to make mistakes. They're inevitable, but we try not to make them. So the only way to reduce type 1 error by itself is to change your alpha level to a smaller number. But in doing that, we automatically increase type 2 error. The only way to reduce both types of errors is to make the curves narrower. And the only way to make the curves narrower is to increase the sample size. Sometimes that's possible, sometimes that's impossible, sometimes this messes with our 10% condition, which means there's only so much we can do to lower our errors. They're always going to happen. We don't know when they happen, but they're inevitable, and we just need to be able to talk about them correctly.